Chapter 4.3, normal random variables and the normal approximation to the binomial. So this gets fun. A lot of this is really just purely in the calculator. So I'll tell you how to type it in. I wish I had a calculator on my screen. I could show you just how to type it in, but I'll just tell you how to type it in. And most of this stuff will be done on our calculator, which is nice. So in this chapter, we'll learn to find probability of events with infinitely many outcomes. So the whole purpose of this is to find probabilities of different events that occur that have infinitely many outcomes. So an example, let's say, you're analyzing the length of call from a sales staff. Calls can be any number of lengths. It could be 2 minutes, 40 minutes. It could be a variety of different things. And if we're going to analyze that data, we're going to use a curve called a density curve. Now, the basic property of a density curve is that it relates probability to area. So what we're doing is sort of visualizing probability. This curve illustrates the more likely probabilities versus the least likely probabilities, and shows us the area kind of in terms of the likelihood of them. So I'll get to that in a second. So if we want to find out, how long what's the probability a call takes between 5 and 18 minutes, we can do that through this method. So let's just say, just to kind of explain this curve a little bit. So I'm going to jump ahead a little and explain this curve. I'm actually going to get a little bit further ahead. We'll get to all that in a second, but I want to get to this curve. Okay. So this curve that you're looking on your screen, this is our normal distribution. So normal distribution has this curve where basically most of the data is centered in the middle. Now, where this comes from, what this stems from, is sort of like, let's take an example of some data. Let's say you go out and you record, you go around in your high school and you record the heights of your classmates. Most of your classmates are going to fall within this middle region. That's, your median range, your average range. There's going to be few students who are really, really tall and a few students who are really, really short. No offense to those really, really short people. Okay. But most of the students are going to fall in some kind of middle ground. And that's why the curve is so large in the middle, because it's absorbing all that data. So let's say, we're looking at student heights, and let's say we found the average height is about 5'8". Okay. And there's some really, really tall people. Let's say this is maybe 6 feet 5 inches, right? And there's some really, really short people. Let's say maybe, what's the difference there? That's 5 and 4, so it's at 9 inches. So 4 feet 11 inches, right? So most people are going to fall somewhere in this middle range. And not, there's going to be a lot of people that are 5'8". Most people, theoretically are going to be 5'8", if that's our average. There's going to be a few people who, of course, are at 5'9", 5'10" range. There's going to be a few people in the 5'7", 5'6" range. But there's going to be a lot of people in that spectrum, right? And there's going to be a very, very small number of people in the 6'5" region and the 4'11" region, right? So that's explaining sort of why this curve is shaped this way. You're going to have more people in this middle, in this average, and fewer people out here on these outskirts. Now, when it's a normal distribution, we always have this sort of ratio, this consistency that you look at on your screen. So this middle part, it says X bar, but we were calling it mu in class earlier, and that's what the Greek symbol looks like. I'm not just making a squiggle. It sort of looks like that. We call it mu. It's just our symbol for average, but X bar is another symbol for average. But that's your mean. That is your average. So the average is stationed right here in the middle, because of course we're expecting most people to be average. And this here is known as the standard deviation. So standard deviation talks about kind of how spread out the data is. So if I go back to, and I don't know why I erased it so much, but let's go back to our height example, and let's say our average was that 5'8". Let's say, and I'll explain standard deviation later, but let's say one standard deviation was 2 inches. Then, one standard deviation up was 5'10", and one down is 5'6". Now, if one standard deviation is 2 inches, that means that 68% of the people surveyed, or at least maybe not surveyed, but in the population, because the survey is just a sample size, 34 and 34, or 68 in total, 68% of our population of our high school, or the heights of these people, is in that range between 5'6" and 5'10". 68% of the people are between 5'6" and 5'10". If we go a second standard deviation out and say, 6 feet or 5'4" right? We're adding another 13.5 and 13.5, which if you add that up, that means in this region, there's 95% of our population. So if our standard deviation, like I said, and I'll explain that a little more later, if our standard deviation is 2 inches, then 2 standard deviations out, ranging all the way from 5'4" to 6 feet tall, that's 95% of our population, because it's a normal distribution. So normal distributions always have this consistency, this reliability. So, and remember, these numbers, these percentages are all based on the standard deviation. Okay, and we'll get to that. And of course, if you go another 2 inches out, 6'2" or 5'2", that third standard deviation, and you add up those other ranges, you're getting between 5'2" to 6'2", you're getting almost 98% of your population is within that region. So only 2% of your people would be taller than 6'2" or less than 5'2". So that's why it's so small there on those ends, because it's such a small number of people that would be in that section, So, but height of people is always a normal distribution. Heights of people are always going to represent in this data, unless you're talking about if you sample like basketball players, obviously their data is going to be skewed a little bit because they're taller. But if you take the average of basketball players, it's still normal distribution. But if you compare basketball players with other people, obviously basketball players is going to be skewed a little bit. But heights of people in general, a normal distribution. A lot of things in life are normal distribution. IQ levels of people are normal distribution. Most people are going to fall in the middle. There's going to be a few people with really high IQ, a few people with really low. But IQ is normal distribution. There's a lot of things that are within this normal distribution, which is why it's such an important curve. And that's why one standard deviation, 68%, 2 standard deviations being 95%, and 3 standard deviations being 98%. These are very commonly known data numbers, and it's very useful for us in determining kind of what the population is in total of these, or the probability of a certain. If I pick a random person, what's the probability that they're this height or whatnot, based on our sample size and our distributions. So back to the beginning though. So this here is a standard normal curve. So it's a normal distribution, but a standard normal distribution always has a mean of 0 and a standard deviation of 1. So you can see, obviously, the center here, that's our mean, our average is 0, and a standard deviation of 1. So that would mean, here to here, that's, as we talked about, 68% of the data. If I went from -2 to +2, that would total up to being 95%. If I went all the way from -3 to +3, that'd be 98% of our data would fall in that region, all the way in that middle. So again, it's the same normal distribution we looked at, but standard normal means that the mean is always 0 and standard deviation is 1. Now in the real world, the mean is obviously something else. Like in heights, the mean could be 5'8", standard deviation of 2 inches. But for a standard normal, it's all based on this very basic normal distribution curve centered at 0 and branching off at standard deviations of 1. So there's these rules for this curve. So what these rules are saying, I'll kind of explain them. Rule number 1 here, probability of z takes a value between a and b, being a less than b, is the area under the curve from a to b. So what's that saying? Z, it's defining z as just the probability. So like, let's say I said a was negative 1.5 and b was positive 1.5. What that first rule says is that, this being a and this is b, and of course, when it says a less than b in that rule, it just means that a is on the left side, b is on the right, so it makes more sense when we look at it, a to b. But anyway, it just says that the area under this curve is the probability. So whatever that area is, that is our probability. That's what, that first rule is basically saying. From this region to this region, our probability is that area underneath. So if I want to look from 0 to 1, the probability of that region is that area. So rule number 2, z bigger than 0 is half, and z less than 0 is half. So this is sort of just saying it's symmetrical in a way. That everything above 0, all of this space here is 50% exactly, and all the space to the left of it, less than 0, is 50% exactly. So it's just saying it's symmetrical. 50% here, 50% here. Rule number 3. So it's also saying symmetrical. So negative a to 0 to a. So let's say that I said a was 1.5. Well, negative 1.5, this region from negative 1.5 to 0 is the exact same as the region from 0 to positive 1.5. That those regions would be, equal in size. So again, it's just saying symmetrical. So if I want to look from negative 1 and negative 2, that's going to be the same as 1 to 2, that those are symmetrical. And for each specific number a, the probability is 0. So this probability only works for ranges. So like I said, this range from 0 all the way up, that's 50%. But if I take it down a bit, obviously this is less than 50%. I think that's 34 from 0 to 1, like 34%. But if I keep taking it and making it smaller and smaller, I'm making this probability smaller and smaller. So maybe now, it's probably like 17%. If I make it even smaller, obviously I'm making it even tighter. So what that last rule says is I pick an exact value, it's 0, because what essentially is happening is those two walls are colliding in on each other. And obviously, if there's no room between them, then there is no area. And if there's no area, then the area is 0. So the probability of any specific spot is 0. Probability is only going to work for a certain range. So here's how you do it on a calculator. On the calculator, if you hit second vars, it says above vars, it says distribute or or something, but it's a distribution function. On there, if you hit second vars, you're going to choose normal CDF. And then it's just going to ask you for 4 values, a lower bound, an upper bound, a mean, and standard deviation. So if you want to find, let's say, the probability of, between 0, let me look at a future problem here. Let's say you want to know the range, the area from 0.2 to 1.2. Well, in your calculator, you would set 0.2 as your lower bound, 1.2 is your upper bound. And for standard normal, remember standard normal means that the mean is 0 and the standard deviation is 1. So you put those 4 values in, 0.2, 1.2, mean 0, and standard deviation 1, and you get that probability. Calculator will just tell it to you. Now, if the calculator doesn't give you a lower bound, or it doesn't give you an upper bound, then you have to use negative infinity or positive infinity. So if you look at number 1, probability z is less than 0.43. Go back to my curve. So 0.43 is probably like right about here. So if I want to know the probability that's less than 0.43, then I'm going to look for obviously all of this space here. But the issue is, and I know it's very tiny, it's hard to see on this picture, but this left side never actually is 0. There's always a little bit of space down there. It technically goes on all the way forever. It's just so small and so minuscule and useless almost that it's, it's almost irrelevant to us. But it does technically go all the way down to negative infinity. Like this side also goes all the way to positive infinity. So in my calculator, if I'm going to try to find the area of this space, well, my lower bound has to be negative infinity. Because I have to, obviously, it doesn't specify a lower bound, it just says less than 0.43. So I have to go all the way from 0.43 all the way down until negative infinity. So my calculator, to type that in, if you type a -1 E99, that tells the calculator negative infinity. Basically, you're choosing a number so small that the calculator will practically think it's negative infinity. So your lower bound in that case would have to be negative infinity. Your upper bound would be 0.43. And of course, since it's standard normal, the mean is 0 and the standard deviation is 1. So you just type those in and the calculator will give you probability. So if it tells you to find the probability of at least being 1.7 or bigger than 1.7, then visually speaking, 1.7 would be something like here. And so if you're talking about all the values that are greater than 1.7, then you're talking about 1.7 being the lower bound and going all the way up to positive infinity. So in that case, the calculator, your lower bound would be 1.7 and your upper bound would be positive infinity. Now to make positive infinity in the calculator, you would type in 1 E99. And again, standard normal curve, so the mean is still 0, standard deviation is still 1. So just remember, if you ever need negative infinity or positive infinity, you're using those. So again, it's negative infinity if it doesn't give you a lower bound. It's positive infinity if it doesn't give you an upper bound. The only other thing is what this formula does is this sort of takes any data and puts it into a standard normal curve, any normal distribution, and converts it back into standard normal distribution. So for example, let's look at the curve with a mean of 10 and a standard deviation of 1.5. Well, let's make it easier. Let's make standard deviation 2. So one standard deviation would be 12 there, and the lower one would be 8. So mean is 10, standard deviation is 2. So again, if standard deviation is 2, that means this would be about 68% in here. Okay. Just to remind you of that probability. So in that case, if I wanted to find the probability between A and B, so I'm just going to, A is our lower bound, B is an upper bound. Let's use 8 as A and 12 as B in this case. If I want to find the probability between 8 and 12, X represents that probability, by the way. And I want to, let's say, I want to convert it into standard normal distribution, because the standard normal, remember, standard normal has a mean of 0 and a standard deviation of 1. So if I want to convert it back into that, then I would follow this rule. All I have to do is subtract the mean from all sides, the middle, left, and right, and then divide by the standard deviation on all sides. So if you subtract the mean, which notice the mean here is 10, so 8 minus 10 would be -2. And 12 minus 10 would be +2. And then divide by the standard deviation. Remember, we said the standard deviation was 2. Divide by the standard deviation, then we would go from -1, because -2 divided by 2 is -1. The middle, I'm just writing this. It's not really too relevant right now. 2 divided by 2 is 1. So on a standard normal curve, the area between 8 to 12 would be the exact same area from -1 to 1 on your standard normal distribution. So remember, standard normal is the same exact curve, but the mean is 0 and a standard deviation of 1. So we talked about that. One standard deviation was 68%. So we know that would be 68% from -1 to 1, just as it would be 68% from 8 to 12. So the reason I'm pointing this out is because sometimes the data we're given is given in this information. So it might not tell us what the mean is or the standard deviation, but if it gives us this little equation or expression, it's hinting what the mean and standard deviation is. So an example, in this problem, a study of reaction times is conducted by repeating an experiment several times with each subject. Let a random variable be defined by assigning a time in seconds to each repetition of the experiment. Suppose x takes the values between 1.28 and 2.54, so that's your lower and upper bound. Find the corresponding interval in which the random variable y, x minus 1.7 divided by 0.42, takes values. So again, all we have to do to find this probability is just use that function in our calculator, the second vars, and then the normal CDF function, right? All it's going to ask us for is the lower bound, upper bound, the mean, and the standard deviation. Now, we already know the lower bound is 1.28 and the upper bound is 2.54. But this is what I mean when I say it's hinting to our mean and standard deviation. This is telling us x minus 1.7 over 0.42. If you remember what I was just talking about on that last slide, you would know that what this is giving us, it's giving away the mean and the standard deviation. The mean is 1.7 and standard deviation is 0.42. So it's secretly telling you those numbers, and you can just plug them into your calculator and the calculator can do the probability for you. But if you don't know that hint that it's giving you, then of course you wouldn't know what these numbers were, and it would make it a lot more difficult. So that's all we're going to use it for, at least in this case. So again, this is just calculator practice. So in your calculator, if you go to your normal CDF, for number 1, you would be typing in for your lower bound 5, your upper bound 15, right? That's for this. And of course, the mean 5 and the standard deviation 10. Type it in, the calculator will tell you what the probability is. And of course, you can change your lower and upper bound to find, between -10 and +10 for part 2. All right. I'm just going to go ahead and skip ahead to the binomial random variable stuff. So for Bernoulli process, we talked about this before in the previous section in this chapter, that expected value for Bernoulli or binomial random variable Bernoulli process is n times p. That's our expected value. For example, if we send out 1,000 surveys and expect 14% to come back, then I'm expecting 140 to get back. That's my expected value. So that same principle is being applied here for our mean. Our standard deviation is this formula. So we didn't really talk about standard deviation in 4.2, but it's brought up here. So this is the formula for standard deviation. Now remember, n is just your number of trials, and p is your probability of success. So let's look at an example. Oh, by the way, this method only works if n times p is greater than 5 and if n times 1 minus p is greater than 5. Don't ask me why, but just take that with a little grain of salt for a second, okay? So here, a Bernoulli process consists of 100 trials with a success probability of 0.2. So basically, you're going to go out and do something 100 times, and you're going to succeed 0.2% of the time. How many times out of that 100 are you expecting to succeed? So let's say maybe you're doing a long jump or something, and you want to make a certain distance, and it's a 20% chance you make that distance. So you do it 100 times, you succeed 20% of those times. How many times did you succeed? That's your mean. That's your expected value. So your mean, if you don't know how to calculate that, it's just your number of trials times that probability, and your mean is 20. So you're expecting 20 successes, right? That's your mean. Our standard deviation, following the same idea here, we got that formula. N times p, which we already know n times p because this was n times p, so that was 20, times 1 minus p, which p is 0.2, right? That will tell us the standard deviation, which I believe in this case is 4. So using just these little formulas and the numbers that it gave us, We know what the mean is. We know what the standard deviation is. So if we want to find the probability that I'm successful somewhere between 25 and 29 times, well, there's your lower and upper bound. So in the calculator, all you've got to do is type in your lower bound, your upper bound, and of course, the standard deviation, the mean and the standard deviation. And of course, it'll tell you the probability. So this just gives you a little more work to do because it doesn't tell you what the mean is right away. You just have to know that the mean is calculated like this and the standard deviation is calculated like that, and you're good. So I'll just go ahead and, I thought it was going to show us. A survey indicates 40% of the voters in Metroburg Airport support a bond issue. 150 people are sampled to ask questions. Let's find the probability that 45 people support the bond issue. At least 45 people support the bond issue. So this again, Bernoulli process, so we're going to use our mean is n times p, which n, our number of trials is 150, and our probability of success is 40%, so that's 0.4. So our mean is 60. 150 times 0.4 is 60. So that's our mean. Again, we're going to type that in the calculator. Our standard deviation is the formula. I'm going to write it up here. It's np and then 1 minus p. Now, I already know n times p. We just calculated that. That's 60. 1 minus p, that's 1 minus 0.4. So just calculate that out. Let me go ahead and do that for you because I don't remember. 1 minus 0.4 is 0.6 times 60. All right, so that is standard deviation is 6. So the mean is 60, the standard deviation is 6. And if I'm asking for at least 45, then my lower bound is 45. My upper bound, because there's only 150 people in total, I'm going to say is 150. And then, of course, you already know your mean and your standard deviation. So type those numbers in the calculator. Calculator will give you the probability. It's something like 99%. It's really, really high, as I think it should be if this makes sense. Because if the average is 60, right? So you're expecting at least half of them to be at least, 60, or a 50% chance that you get at least 60. And a standard deviation is 6, which is not a very high standard deviation because 45, if you look at it, it's 15 below 6 or below 60. That's over 2 standard deviations away, which is a good distance away. So 99% makes a lot of sense to me here. That's, I believe, what the probability what the calculator gives us. So I'm going to wrap it up. Sorry if it was a long video, but I'm just trying to help. Okay. See you in the next test. Okay. Bye.